Okay, good morning. Now it's my great honor to introduce you Professor J.D. Jackson from Manchester University. Professor Jackson is a very famous professor in the field of heat transfer, and he made a great number of publications and gave many keynote lectures in the international conferences. Since 2003, Professor Jackson became the guest professor of Tsinghua University, and every year he comes to Tsinghua and visit us and give lecture for students and to discuss the research with our graduate students. And he made great contribution to our development and research. Now welcome Professor Jackson to give us lecture.
Well, it is a great pleasure to be here to talk to you this morning. And as you can probably see, I'm from the University of Manchester in the UK. The School of Engineering at Manchester University was the first one in the UK. And the first professor of engineering in the new chair was Professor Osborne Reynolds, whose name is associated with fluid mechanics through the Reynolds number. And today I'm going to talk about the Reynolds number, where it came from, and give you some background. I'll give you a little bit of a picture of Osborne Reynolds. Now what's going on here? Nothing's happening. Ah, yes. Biographical overview. By the way, I'm going to talk as slowly as possible, but I haven't got a lot of time and some interesting things that I want to talk about. So maybe I'll have to try to avoid talking too quickly. But I will give you a biographical overview. Osborne Reynolds was born in 1842, and his father and grandfather and great-grandfather were rectors. That means part of the Church of England. They were the local priests, if you like, in the Anglican Church. And he lived in Suffolk, which is not far from London, 70 or 80 miles from London, but in the countryside. His father was also called Osborne Reynolds, and he was a fellow of Queen's College, Cambridge. That means he graduated in mathematics at the University of Cambridge. So his father was a mathematician. But he was also a rector. That means he ran the local church. He was in charge of the church in this village. The village has a strange name, Debech with Bulge, a very English-sounding name. Now, his father was also a headmaster of a local grammar school, a very well-known grammar school at that time. And he eventually had also a part-time job as rector of the local church. So that was the background to Osborne Reynolds. And they lived in a nice house with a big garden, and they owned farms all the way around. So they were reasonably rich. Not very rich, but reasonably, very comfortable, I would say. Now, so that's his house. His early education, the young Osborne Reynolds, his early education was undertaken mainly by his father, because his father was a teacher anyway, and his father was a mathematician. So it's not surprising that Osborne Reynolds, the young Osborne Reynolds, grew up with some interest in what am I doing now? Yeah. He grew up with some interest in mechanics, applied mathematics, really. So even when he was a teenager, he was interested in mechanics, applying mathematics to practical problems. When he was just over 20, his father sent him for some practical training to a special school attached to a manufacturing firm. And he lived there for between 1 and 2 years, learning practical skills. So he'd already been educated by his father in mathematics. Then he got practical skills in this school, which was run by a man called Edward Hayes in Stony Stratford. And then Osborne Reynolds decided to go to the University of Cambridge to take a degree in mathematics, because he'd become convinced that in order to be an engineer, which is what he really wanted to be, he must be very good at mathematics. At that time, it wasn't possible to study engineering at a university in the UK, but you could study mathematics at the University of Cambridge. Cambridge is the best university in the UK. I like to think why. It's a leading establishment. And Osborne Reynolds had a very successful academic career. He got his degree, did very well, was one of the best students who graduated. And so the college that he lived in, Queen's College, Cambridge, elected him as a fellow. So he became part of the establishment of the college. And he then entered in London the office of a well-known civil engineer, John Lawson, in London, to get some professional experience of civil engineering. He only stayed there for a few months because there he was, that's how he looked at that time, in his 25 years old by then. He only stayed there with the civil engineering consultant for a few months, and then a chair was appointed, a new chair, the first chair of engineering in England. And this was at what is now called the University of Manchester, but in those days it was called Owens College, Manchester. So he was interviewed and was successful. And in his application he explained why he wanted the job. He said from his earliest recollection he had had an irresistible liking for mechanics and the physical laws upon which mechanics as a science is based. And he said, in my boyhood, I had the advantage of the constant guidance of my father, who was also a lover of mechanics and a man of no mean attainment in mathematics and its applications to physics. So that's his background. He grew up learning mathematics from his father, graduated at the University of Cambridge, had had some almost 2 years practical training, a brief experience, professional experience, and then he applied for the job at Owens College, the first chair of engineering in England. And, well, he was successful. Those were members of the interviewing committee. Just imagine sitting in front of those guys and trying to, at 25 years old, trying to convince them that he was the man for the job. But he managed to do it. Now, he appointed to the chair, he took the chair up in 1868 when he was just 26 years old. And he stayed there in that chair until 1905, all his working life as Professor of Engineering at the University of Manchester. And he died, after some retirement, he died in 1912. This was what's called the Victorian period in the UK. Queen Victoria, the Queen of England, very well-known queen. This was an interesting time in the history of England. It was also a very interesting time in the history of science. Some very important scientists were working in England on various aspects of physics and engineering at that time. I'll mention some of them in my talk. Now, he got a number of degrees and honours in his career, naturally. He was a really outstanding engineer scientist. So, various degrees and honours. When he was appointed to the new chair, he had to give his inaugural lecture, the first lecture of the year to open the new academic year. They took the new professor and said, you talk to us about what you're going to do here at Manchester. And his lecture was entitled, On the Progress of Engineering Considered in Relation to the Social Condition of this Country. Now, it's a very interesting title. He was a serious guy. He wanted to really do something through his engineering knowledge to contribute to to improve the social conditions of his country. Now, what you must remember is that engineering as an activity began in Manchester. The Industrial Revolution first happened in Manchester around about the year 1800. And then it spread around the world. But engineering as an industry began in Manchester. And Manchester was a small town, almost a village, in 1800. By 1850, it had over 1 million population. So it grew very fast. The industry was very important, but also very dirty. Manchester was one of the dirtiest places in the world by 1850 because of the industry and the pollution. All the problems which you have faced in China were there in Manchester in this early period of its development as an industrial city. And it wasn't until 100 years later, 1950 or so, when I appeared in Manchester, that people stopped burning coal and the city became clean again. The University of Manchester, the building was black, but the stone was a nice colour. If you washed it, underneath it was yellow. But it was black as coal when I went there in 1950. Now it's clean. We've washed it. So, some interesting parallels between Manchester and its industrial development and the industrial development in China. Okay, now, his academic career, he did a lot of research. And I haven't got time today to tell you about all of it. I'm going to skip through many, many slides. And most of them I don't have time to talk about. I want to concentrate later on what he did in the way of a contribution to engineering fluid mechanics, because that's what I've decided to talk about today. And so I will be skipping a lot of the material I've got on this presentation. I would need about 2 hours to do the full presentation, and I haven't got that kind of time. Now, so he did a lot of things. And he worked in parallel streams. This is time, from 1868 through to 1900. And these are the parallel streams of activity that he worked in. He was very wide-ranging in physics and engineering. And I'm going to talk today mainly about his contributions to fundamental fluid motion and turbulence, which took place over about 30 years and began fairly soon after his career started. He modelled himself on a man called Rankine. Now, Rankine was Professor of Engineering in Scotland, not England, in Glasgow. That was a centre of shipbuilding development, and engineering had grown in Scotland, in Glasgow, because of shipbuilding. And Rankine was the professor there. He wrote pioneering books, some very important books on thermal power and other aspects of engineering, which Osborne Reynolds was very impressed with and educated himself by reading. Now, Reynolds' early work, the time Reynolds arrived in Manchester, this Owens College was a fairly small outfit, and its building was quite small. There was very little in the way of laboratory space or anything like that. If you wanted to do experiments, you had to do them at home or outside, and that's how he found himself in the first few years of his working life. There's a drawing of the building. Not very impressive at all for what became the University of Manchester. But within a few years, they built this nice new building, and that's the University of Manchester. That's how it looks now. Of course, it's much bigger than that now, but that's a central part of the University of Manchester. And Osborne Reynolds had an office just through this door inside of there, and that was the engineering department. Right. Manchester had a famous society, the Manchester Literary and Philosophical Society. It had been established before 1800, and one of the first presidents of that society was a man called Dalton. Now, there's a law called Dalton's Law of Partial Pressures, Dalton founded gas chemistry in Manchester. He was a very important chemist. And Dalton was president of the Literary and Philosophical Society, and then later another president of the society was a man called Joule. Let me go back. Joule. Now Joule, the unit of energy is the joule. Joule was a scientist who lived in Manchester, and the first law of thermodynamics was proposed in Manchester by Joule. So we already had some important people in science there in Manchester before Reynolds. Reynolds joined the Literary and Philosophical Society, and the president at that time was Joule. There is Joule, the founder, the first law of thermodynamics. So a very famous fundamental law in physics was proposed by Joule. Now, the first lecture that Osborne Reynolds gave, the first paper he presented to this society, was on this interesting problem of the stability of a ball mounted on a vertical jet of water. And it spins round and it throws off droplets. And it's stable. So you can take a table tennis ball and do this experiment yourself. And it's beautifully stable. It sits off-center from the jet. And there's a balance between the momentum of the droplets and the pressures and this kind of thing. But explaining it is complicated. There are surface tension effects involved. And Osborne Reynolds explained this in his first paper. Now, he'd been appointed as the first professor of engineering in order to help the local industry. But what he was doing was fiddling around doing silly fluid mechanics. And I don't think those guys who interviewed him, who you saw earlier, were very impressed by his first paper. However, he went on to do some very important things. Now, he studied out-of-door physics because he didn't have a laboratory. So he did a lot of simple experiments, and I haven't got time to go through them, but it was described as out-of-door physics by one of his students. One of his students was J.J. Thomson. Now, if you know anything about physics, you will know that J.J. Thomson discovered the electron, and he was one of Osborne Reynolds' students in mechanical engineering. But eventually he switched from engineering to physics and became a very important scientist himself and discovered the electron. But he was one of Reynolds' mechanical engineering students at one time, when he was still a young man. Now, Reynolds did a lot of experiments on out-of-door physics, and I haven't got time to go through them, but that's the solar corona, modeling of the solar corona. That was some interest to people at that time, general interest. And he looked at the action of raindrops in calming waves on the sea and did some experiments with droplets falling into pools. That's a diagram from his paper. He looked at the formation of a hailstone. That's a perfect hailstone. He explained why it has that shape. He reproduced hailstones himself in a simple experiment. There it is, a reproduction of it. He explained why the trees blow apart when there is a thunderstorm and electrical lightning strikes. It's due to the boiling inside the water inside the tree, which blows the fibers apart. And he did an experiment. This is a modern reproduction of it, but he did an experiment to explain it. The effect of oil in destroying waves on water. Now, this is one, he did some experiments on this. If you throw some oil onto a pool over which the wind is blowing, the oil can have the effect of stopping the waves. And he was very interested in that. In fact, he got some very important ideas from that about the way in which turbulent eddies are born underneath the surface, because that's the reason why the wind doesn't produce waves. The energy goes into the production of turbulent eddies. Now, I really haven't got time to go through this, but I'm just giving you a flavor of things that he did. He became interested in the way in which eddies are born in a flow. It was well known at that time that flows could either be direct or sinuous. People didn't understand it, but it was well known from common experience that there were two types of flow. laminar or turbulent, but they were called direct sinuous. He was interested in how turbulence is formed in a shear flow. And that can be either stable or unstable depending upon the flow rate. They knew that, but they didn't know why. He looked at this. This is a very unstable thing. Such a flow can never be direct. It always becomes unstable. So he was interested in this kind of thing. And he did a simple experiment with two fluids inside a glass vessel. Two fluids of different density. And by moving the thing this way, he produced a counterflow of the two fluids and looked at the stability. In one case, he got waves on the surface. And in the other case, when a skin formed on the surface of this chemical, he didn't get waves, he got turbulent eddies underneath. So he learnt about turbulent eddies from early experiments, very simple ones. That's a picture of a letter that he wrote where he was talking about the effect of oil on water in calming waves. He describes an experiment that he'd done, throwing oil on water. Of course, he couldn't do that experiment these days. You're not allowed to do things like that. But in Victorian times, you could do anything. And so he studied that problem experimentally. And that's one of his colleagues, a professor of mathematics at Manchester, Horace Lamb. There's a very famous fluid mechanics book, Lamb's Hydrodynamics, which is not used so much these days, but 50 years ago it was still in very common use on fundamental fluid mechanics. You'll find it in your library. He did all kinds of simple experiments. Cavitation, the boiling of water due to pressure change. There's my attempt to reproduce his experiment. Dilatancy of granular materials, sand. If you go to the seaside and walk on the wet sand after the sea has gone out, put your foot on the wet sand, what you will find is it goes dry around your foot. Everybody who's done this knows why, when you press on the sand with your foot, on the wet sand, does it go dry around the foot? Just the reverse of what you would expect. It's because of the rearrangement of the particles, which are normally like that, but when you shear them by putting your foot on, they go like that, and the space increases. It draws water underneath your foot. That's a very interesting phenomenon. And he did experiments to explain that. There's his experiments to explain it. He did research on the physics of gases. The kinetic theory of gases was new at that time. There was a very famous scientist in the UK, his name was Maxwell, who was pioneering these ideas in physics, explaining the physics of gases. But Reynolds also worked on the same topic and produced some very important paper, one particularly important paper on that topic. So he worked in physics as well as engineering. That's Maxwell. He was at the University of Cambridge. So Reynolds did experiments and did theory on the on physics, on the kinetic theory of gases, and that's one experiment that he looked at. I haven't got time to discuss that. But you can see some interesting things he did in this area of physics. The thermal transpiration, that is the flow of a gas through a porous medium because of a temperature gradient which is present, is a very important physical phenomenon. And he looked at that and did the theory and also did an experiment to validate his theoretical ideas. Flow through a porous plug by creating a temperature difference across it. So, kinetic theory, and then he went on, he was also working on applied hydrodynamics. That's the stability of ships. And this, he worked on the propulsion and the stability of ships. He also worked on flow of rivers in estuaries, where the rivers flow into the sea, the transport of sedimentation. He produced the scaling laws for that particular phenomenon of transport of material by the sea. That's ship propulsion and dynamics. That's from one of his papers. then the modeling of rivers and estuaries, and there's a scaling law that he developed for enabling you to do an experiment in the laboratory to simulate the behavior of a river. Very important contributions. There's one from one of his papers. Now, pumps and turbines. He developed pumps and turbines. And he was the first person to work out how to multi-stage pumps and turbines, having a rotor and a stator, And he patented that idea. So the modern steam turbine is based on this idea. All our electricity is produced in steam turbines, in devices like that. He was very much a physicist, engineer, and combining the two things. There are some models of pumps and turbines. That's a multi-stage pump that he produced, and there's his little two-stage radial steam turbine. So he was very much an engineer as well as a physicist. There's his steam turbine again. And there's the brake, the dynamometer, which was used. He was contemporary with Froude. Froude was a well-known engineer scientist who worked on hydraulics. Now, Reynolds also worked out the theory of hydrodynamic lubrication for bearings in a very important paper. And he explained why a bearing is able to work with very simple diagrams, but he did the mathematics of it as well. So he laid the foundations of lubrication theory. And there's a demonstration of a bearing. Reynolds' analogy, in 1874, only a few years after he was appointed in 1868, and in 1874 he published a short but very important paper on the relationship between turbulent heat transfer and pressure drop in a tube. He was applying this to steam locomotives, to railway locomotives, and the boiler has tubes along which the exhaust gases flow and give up heat to the tubes and cause the water surrounding them to boil, produce steam. He did some very important idea on the relationship between the pressure drop and the rate of heat transfer in tubes. And he explained that the most important reason why heat is removed from a heated surface is because of turbulent eddies, which transfer the heat across the thermal layer. The transport of energy, thermal energy, by turbulent diffusion is the real reason why we can transfer heat from surfaces. Molecular diffusion is not effective, but fortunately we have turbulence present in most engineering flows, and that carries the heat across the boundary layer. Very important phenomenon. There is the Reynolds analogy between pressure drop and heat transfer. Reynolds analogy. Flow visualization using dye streaks. He was very interested in visualizing flows using ink and vortices and interesting flows. He did a lot of experiments like that and published papers on it. So he developed visualization techniques. And thus, the scene was set for him to make further contributions to the understanding of turbulent flow using dye to visualize turbulence. Now, inertia and viscous effects. You already know about the Reynolds number. Professor Zhang said you've heard about the Reynolds number already. Now, but I just want to talk for a few minutes about the physics of it. What does it mean physically? Where did Reynolds get his ideas from? What are they based on? Well, one of the starting points was the work of Stokes. You've heard of Stokes, viscous flows. Stokes. Now, Stokes was a professor of mathematics at Cambridge. He taught Reynolds. So Reynolds had learnt about fluid mechanics of viscous flows from the guy who wrote down the Navier-Stokes equations. Navier in France was also doing the same kind of thing as Stokes, and we now talk about the Navier-Stokes equations. But they both wrote the equations down for viscous flows. And so Reynolds knew about those equations. He'd learned it at university from Stokes. And so he was able to look at the Stokes equations and say, inertia term, viscous term. This term is due to inertia. This term is due to viscous shear. Let's look at the ratio of these two terms. And there we have the ratio of the inertia term to the viscous term. And when you cancel things out, that's what you get. And that is the so-called Reynolds number. And that's how he got to it, from simple mathematics, by looking at the governing equations for viscous flow. But he also noticed that this thing here, the kinematic viscosity, molecular diffusivity, that's what it is. The kinematic viscosity is related to the diffusion of momentum by molecular transport in a velocity gradient. Molecular diffusivity. And he said, oh yes, I know something about gases, kinetic theory of gases, and I know from kinetic theory of gases that this molecular diffusivity is a product of two things. It's a product of the molecular velocity and the mean free path. And this thing on the top is the product of the velocity of the flow in the pipe and the diameter of the pipe. These things are related. The physics of the Reynolds number there is to do with turbulent diffusion on the top and molecular diffusion on the bottom. And they're both, that thing is just the molecular velocity times the wavelength. And that's the macroscopic velocity times the pipe diameter. Very interesting interpretation of this stuff. So there's a lot of important ideas on these few slides that I'm putting up at the moment. I produced this before breakfast this morning for you. You'd be interested to know. This is something I only included because I was giving this talk this morning. So I've talked already about the molecular diffusivity, and he saw UD as a characteristic turbulent diffusivity, which it is. Now, direct and sinuous fluid motion. It was well known at that time that there were two types of flow. Even in the 1850s, there were scientists who were trying to visualize flows. There was one whose name was Hagen. It was a German, I think, or Belgium, I'm not sure. But he did experiments to visualize flows to show direct flow, laminar flow, and turbulent flow by throwing sawdust. When you cut some wood, you make wood and dust. He threw this into the water, and he was able to see by the motion of the dust in the water what the fluid was doing. So Hagen did flow visualization with sawdust and water in the 1850s. It was well known that there were two types of flow. I've already mentioned that Stokes was professor of mathematics, and I've talked about this already, and that Reynolds knew about the mathematical equations. And he also had this interest in connecting eddies with transferring heat across boundary layers, and he knew that eddies also affect the pressure drop in tubes, affect the turbulent drag. So these ideas he was familiar with. I mentioned earlier the analogy between heat and mass transfer. It happens to be spelt out on that transparency, so I won't go through it again. And so in 1883, by 1883, he knew a lot about the physics of turbulent flows, and he'd done some classical experiments. And in 1883, he published the paper that everybody in fluid mechanics knows about, in which the Reynolds number appeared for the first time. And it was a classic. It remains a classic in the literature of the science of fluid motion. And his work in that area had a profound effect upon the development of fluid mechanics in the widest sense. Now, there's, I mentioned already, he did work on the visualization of flows with ink. He used it to visualize laminar and turbulent flow. He did better experiments than Hagen had done earlier. And he did them on this beautiful experiment. If you open most textbooks on fluid mechanics, you will find this picture. It's taken from Reynolds' paper in 1883. The illustration was produced by called a woodcut. Somebody carved this out in wood and made prints. That's a woodcut picture of his experiment. And the experiment's a kind of fish tank up here, which is full of water. And the water can flow from the fish tank down a glass tube and out to the drain if you open the valve. So we can get flow along a glass tube out of this tank. And it can be very steady because the water is settled and very steady in the tank. So this is an experimental arrangement which is ideal for looking at laminar flows. So it was 6 feet long, 18 inches deep, and 18 inches wide. The picture is not a very accurate representation of the actual thing. And this piece of equipment is still there at the University of Manchester. I'll show you a photograph of it in a moment. And one side of the tube, this glass tube, was connected to an iron pipe which went to the drain. So water could flow through this trumpet and down the glass tube. And you could, if you put some dye in here, you could get a streak of dye flowing with the water along the tube. So you could visualize the flow. So this is just, these pictures are just telling you how it operated. He needed to know the flow rate. And he did this quite brilliantly by having a float which floated on the surface, the free surface of the water there. So as the water flowed out of the tank and down the glass tube, the surface level was falling slowly. That was connected by string to a pulley, and it turned a dial round. And by measuring the time taken for the dial to rotate, he could measure the flow rate of water out of the system very precisely. And there's the tank, the Reynolds tank, as it is, more or less as it is these days. Although this picture, this photograph was taken in 1968, when I organized a big conference in Manchester to celebrate the centenary of the appointment of Osborne Reynolds, 100 years after his appointment. And there is the tank, which was on display at this symposium, and there are two of his former students. Those guys were taught by Osborne Reynolds. They were still alive in 1968 when I took that photograph. Now, when he did the experiments with the tank, when the flow rate down the tube was slow, with a low flow rate, the dye went in at that end and went in a straight line along the tube. That is direct or laminar flow. That diagram is from his paper. But if he increased the flow rate, things changed. And at a critical flow rate, which depended to some extent upon the external disturbances that are present, the dye remained stable and then appeared to diffuse like that. And that was the effect of the flow changing from being laminar to turbulent. And it looked as though the dye, all the water had gone blue. But in fact, if he put on a light source which fluctuated, then that's how it looked. And the dye rolls up into like a ball of wool. That is what is really happening in turbulent flow. And he demonstrated this by having a fluctuating light source, so he could see this. You need a fluctuating light source. He did this by an electric discharge of electricity to produce a spark which fluctuated. Really brilliant experiment at a time when equipment available was very, very limited, but he was able to demonstrate what turbulent flow really is like. Well, there's the Reynolds tank again, and if you were stood up here with me, you could probably see laminar flow down that pipe. It's impossible for you to see it, I'm afraid. It's very difficult to photograph it. And there's turbulent flow. But as I say, you can't see it from where you are. So he then set about, he was looking there at the onset of turbulence, the way in which turbulent flow, laminar flow becomes unstable and the conditions under which it becomes unstable. And what he found in doing those experiments, he varied the size of the tube, varied the diameter, he varied the temperature of the water to vary the kinematic viscosity, and he varied the flow rate. By varying those three parameters, he found that the Reynolds number, velocity times diameter divided by kinematic viscosity, correlated the results. So this was the first demonstration that the Reynolds number is a unifying parameter, and it can unify the correlation of transition from laminar to turbulent flow. Now, a very important idea. But it's also, he was interested in what is the value of the Reynolds number below which a flow will always be stable, no matter how big are the disturbances. There is a critical value of the Reynolds number below which, even if you put a lot of disturbances into the water, the fluid is stable, the disturbances are damped out, and the flow remains laminar. So he set about a different experiment to study that problem. This is called the lower critical Reynolds number, the one below which the flow is always stable. And so he used very disturbed water flow. I'm afraid you probably can't see this very clearly. There's too much light in the room. But what he had in this experiment was a horizontal tube fed by water from the mains with a lot of disturbances in it. And he measured the pressure drop along a length of pipe. And he measured the flow rate by collecting the water. And he produced graphs of pressure drop against flow rate. He did it for several different tubes, different flow rates, and there are two graphs of pressure drop against flow rate. And what you find is that at some point there's a change in the behavior. The slope of the line changes. That is, below this condition, the flow is stable. Above it, it's turbulent. So he was able to determine the condition below which a flow in a pipe, no matter how big the disturbances are, it remains stable and laminar. And what he did experiments with different pipes and different flow rates and varied the temperature, and he established that this changeover occurred at a critical value of the Reynolds number, about 2,000 for a circular pipe. So that's where the value of 2,000 for stable laminar flow came from pressure drop experiments. And so he correlated the results in terms of his dimensionless group, which wasn't called the Reynolds number in those days because nobody else knew about it, although he published the papers. But the term Reynolds number came very much later. I'll explain later when it first came. Took a long time for the rest of the world to understand what Reynolds had been doing. Now, okay. But what he found was that if he took the pressure drop, divided it by the dynamic pressure, and got the friction coefficient, and if he plotted it against his Reynolds number, he found that all the results lay on one curve. Everything for different pipes, different flow rates, correlated. Friction coefficient was a function, that's the dimensionless pressure drop coefficient, it's a function of a single parameter, the Reynolds number. Now that was the biggest step that was ever made in fluid mechanics. Is that the end of my talk? Okay, I'm not far off the end anyway. I'm getting to the interesting part now. This is a very important result, okay? To bring together all the experiments that anybody could do around the world with different fluids, not just water, air, any fluid, any pipe, they correlate that way by a single relationship. Now that is the reason why we can, these days, do design in fluid mechanics, because we have simple equations which are general, and it all came from these experiments of Osborne Reynolds. But he went further than that. He actually fitted an equation to the relationship, a power law. Now that equation is usually attributed to Blasius, a German scientist, who did his work in 1914. However, this was published by Osborne Reynolds in 1883. So he was way ahead of his time. And these ideas got lost for very many years before other people picked them up and started to run with them. N has the value about 0.27 for smooth pipes. But if you have a very rough pipe, N is almost 0. So for a rough pipe, the relationship is, friction coefficient is almost constant. So these are important ideas, and arrived very early as a result of the work that I've been describing to you. Now this paper was refereed by Stokes before it was published, and it was also refereed by Rayleigh. Rayleigh is a very important scientist. You may have heard of the Rayleigh number, but later in heat transfer you will learn about Rayleigh. He was an English scientist at the University of Cambridge, and Rayleigh and Stokes refereed this paper of Osborne Reynolds and were very impressed with it. It all went through and was published in the Proceedings of the Royal Society. And Rayleigh said that in his appreciation of the paper, he said, Professor Reynolds has traced with much success the passage from one state of things to the other and has proved the applicability under these complicated conditions of the general laws of dynamical similarity as adapted to viscous fluids by Professor Stokes, a subject which is certainly second to none in scientific as well as practical interest. Now that was said by the referee of the paper, and it's perfectly true. Everybody accepts that this was a brilliant contribution to science. And engineering fluid mechanics is based upon this idea. Now, there's Lord Rayleigh, very sort of impressive guy. Now, this was 1883. Reynolds then went on for another 10 years working on the subject and trying to do some theory, because he'd been doing all this by experiment mainly and physical intuition. And so he went on and he managed to write down the governing equations for turbulent flow. And you will learn about this later perhaps, because in a turbulent flow, as well as having viscous stresses, you have turbulent stresses. And these are now called the Reynolds stresses, because he was the first person to identify them mathematically. And in 1994, he wrote this paper on the dynamical theory of incompressible viscous fluids, which wrote down the theory for turbulent flows. And you know, these equations and the ideas involved in those equations are used as a basis now for most of the computational work which is done to predict fluid flows, turbulent fluid flows. So there's been this tremendous development of CFD, as it's called, over the last 50 years or so, but it's based upon ideas which came from Reynolds' paper in 1894-95. So, the results of the theory I've mentioned, turbulent stresses. Also, he wrote down the turbulent kinetic energy equation and showed that there's a balance between production of turbulence and dissipation of turbulence, and this defines the condition for stability of laminar flows. So he did it all, and there he is at the time that he'd done all this valuable work, looking a bit tired, like me, more than a bit tired, but he'd done a lot of work. There he is teaching his students. These pictures were drawn by one of his students in the lecture. There's the equations of motion on the board, and he's scribbling away, not taking any notice of the students at all. And he was a lousy teacher. He was the worst teacher ever. but very stimulating. And there he is doing an experiment in the lab, looking a little bit happier. And there he is having to talk to the students. And there's the student, pretty damn fed up with what's going on. Nothing's changed in 100 years. There he is with his students, there's Osborne, some of his students, in 1903. The Reynolds number, it wasn't used, it wasn't called the Reynolds number until 1908. And there was a scientist called Sommerfeld in Germany who was interested in the stability of flows, the mathematical stability of flows. He first discovered Osborne-Reynolds' work and said something about it, and called it the Reynolds number. There was a famous scientist later, well, there's an article about all this written by a guy from Stanford University, and in 1913, Prandtl, another big name in heat transfer, also used the term Reynolds number. So it took a long time before these German scientists, around about 1913, began to recognize the work that had been done. But in England, there was a guy called Stanton. And in heat transfer, you learn about the Stanton number. He was one of Reynolds' students. And eventually, he stayed on and did his master's degree, and then he did his doctor's degree, a Doctor of Science, working for Osborne-Reynolds. He knew all about this, but he never told anybody else. So Stanton was one of Reynolds' students. So we have the Stanton number, Reynolds number. These are very important names in heat transfer. There's Stanton. Okay, concluding remarks. The success of Osborne-Reynolds in identifying the fundamental dimensionless parameter which characterizes the behavior of flowing fluids was without question a pioneering achievement which many people regard as his most valuable scientific legacy. But he did a lot of other things as well. His experimental work on the circumstances which determine whether a flow is laminar or turbulent, combined with his dynamical theory of turbulent flow, together provided the foundations for the subsequent development of fluid mechanics. And that's the end of my talk.
Do you have any questions? Any questions, any comments?
You're welcome to ask questions, but I don't expect you to really have time. I've thrown a lot of ideas at you, but some of these are very important ideas. And as you learn more about fluid mechanics, you will realize that this stuff really is important. But you know, it'll take time for you to learn about fluid mechanics. I was your age in 1952 when I first came to Manchester. And the first thing I saw when I entered the laboratories in Manchester was the Reynolds tank. And I've been fascinated by the work of Osborne-Reynolds ever since. And that's why I'm giving talks like this sometimes, although I do talk about other things as well. But I thought this would be something which you would enjoy, and later, when you learn more about fluid mechanics and heat transfer, you will remember some of the things that I've mentioned to you today, I hope.
Okay, thank you very much, Derek Jackson.
Okay.
Thank you. Okay, 那我们休息一会儿，7点钟嘛。